My name is Anders Christensen from the KGSEA Math Circle, and today I'll be explaining LLM architecture. So before I begin, I'd like to give a broad roadmap of what I'll cover today. So this will cover all the major steps of LLMs, including tokenization, embedding, the transformer core, as well as the output layer. And by the end, hopefully you'll have a better idea of what's going on behind the scenes, under the hood, and how your prompt gets turned into GPT text. So first, tokenization is the first step. And this is where text gets split into tokens that the LLM can process. So LLMs can't process characters or words directly, but what it does is it splits them into tokens from a fixed vocabulary. So for example, if the vocabulary has a word like this, then it'll identify that in the sequence and then encode that as it's going to give it a numeric ID. And it's important to note that tokens don't always have to be full words. More often than not, they're often subword units. For example, the word don't, the contraction don't, might be tokenized as do plus apostrophe NT. And so the tokens are given these numeric IDs, and you can think of that as analogous to like the atomic number of elements. For example, hydrogen has atomic number 1. And this, for example, in this tokenization scheme, has an ID of 2023. So once all these tokens have been converted into numeric IDs, it's mapped onto a learned vector space, and these vector spaces are very high dimensional. For example, for the OpenAI text embedding large 3 scheme, there's around 3072 dimensions, so it's a very large vector. So the parameters for these vector spaces are decided randomly when it first starts, but the parameters are adjusted and fine-tuned during training. So what do these embeddings represent? So they represent a lot of things, but some intuitive ways that we can think about it is as representing semantic similarity. For example, we can kind of intuitively know that through analogies that man to woman is king to queen. They're kind of similar. And if you take the vector distance between those two vectors, then they're pretty similar between man and woman and king and queen. So you can kind of think of that particular dimension as encoding for gender. Embeddings can also represent syntactic and grammatical patterns. For example, walking versus walked, swimming versus swam, that kind of encodes verb tense. But it's important to note that at this stage, the embeddings don't have any context, right? So homophones, words that have multiple meanings, like for example, duck, the verb as in like, ducking, and duck, the noun, like the animal, are not considered distinct at this stage. And also it's important to note that token positions are also added to these embeddings, which basically represents where in the sequence this token is located. So what happens when we don't have any context? What happens when one vector can encode for multiple different meanings? So in embedding, the vector as I illustrate with this example, the vector for all four contexts of the word mole is the same, like mole the animal, mole the unit, if you've taken chemistry, like, on your face, also, mole, a common Mexican dish. But we want to be able to encode the meaning of all these different contexts. And transformers, which is the key part of how these LLMs work, is going to help us do that. So transformers, you can think of it as a series of layers. So these layers are going to repeatedly refine the token representations. For example, if we go back to this example, if you have a sentence and it has a mole, mole as an animal, if that's the context, then the transformer is going to repeatedly change the vector encoding for that particular token to more accurately represent the fact that it's an animal, it's a mammal, it lives underground, and so on. So here I'll introduce a concept called attention. And attention is an incredibly important concept in machine learning and these transformers. You can think of it as a method for determining which words are important and which words are not. For example, if we're talking about moles as in the animal, some words that might give it context might be, underground, burrow, mammal, and so on. And other words that we don't care about as much, just grammatical parts of the sentence, for example, are given less weight. So I'll briefly explain the architecture of the transformer. So the transformer consists of an encoder and a decoder, and these are basically the same thing. They're basically just devices for reading tokens. But encoders, the difference is that encoders see tokens from both direction, like it sees tokens forward and backward. And these are widely used for tasks like translation. But the important thing is that decoders see only past tokens, so they only receive information in one direction. And modern LLMs like ChatGPT or Claude only have only decoders, because if you think about how an LLM generates text, it generates from like front to back. So it's not really bidirectional, but I figured that you should also know what an encoder is. So let's look at the specifics of one transformer layer. So each layer consists of a masked multi-head self-attention and a feed-forward network, also called a multi-layer perceptron. So you might not know what that is, but I'll explain what each part means. So self-attention is basically, as I said, it's a method for determining the value of each word. And it's called self because we're not programming this in, we're not labeling data manually, but it's self-trained. So it's going to look at other words relative to itself and determine the attention that way. So each token for each layer produces three vectors that we care about: the query, the key, and the value. So the queries are compared to the keys, which is multiplied to value to get the attention. So the actual formula itself is more complex, but for now, this is an easy way to think about it. So to illustrate, I'll give an example. Imagine two sentence fragments, and we're going to use this attention algorithm to better represent the context of Harry. So the Duke of Sussex, who married the insufferable actress Meghan Markle, Harry. So this is like a descriptor for Harry. And the second sentence is the boy who lived and became the greatest wizard, Harry. So if it helps, this is kind of a helpful mnemonic, but in this sentence, Harry is the query, and all the other words are keys. For example, Duke, Meghan, Sussex, or boy, wizard, lived. And so we're going to compare the relationship to query and key. And this is through like vector multiplication, like the dot product. And if you think about it geometrically, a higher dot product means, the vectors are kind of facing a similar direction, which means the meaning is kind of related. So basically, if in the first sentence, Harry has a high dot product with Duke, for example, then the attention is going to reflect that fact because, the query versus key relationship, those with higher values are given more attention. And then this is just kind of specifics, but a process called softmaxing is applied to make all the attention add up to one. And this is something we'll see later when we get to the probability distribution. So that's basically what self-attention is. Now, multi-head attention, which I also described as another one of the steps in a transformer layer, captures multiple different attention mechanisms at once. For example, language is an immensely complex thing, and there's a lot of different rules that are going on at the same time. For example, there might be, noun adjective agreement, there might be, gender, and so on. And so these multi-head attentions, they all look for different patterns. But it's kind of hard to pinpoint a specific feature to each head. But you can think of it as a bunch of attention modules running at the same time, trying to find different different parts of different linguistic features. So now comes an important step called multi-layer perceptron, and this is after the attention step has been completed. So if you've done, neural networks or, deep learning, this might be familiar to you. So, but the data from the attention step is input into the input layer as an integer, and it passes through several hidden layers where more feature extraction happens. And something called an activation function is applied to introduce nonlinearity, because if it was just linear, it would be pretty simple. You would get the same answer every time, and language isn't really a linear thing. And it learns via a process called backpropagation. So it'll try and minimize the loss by testing it. I won't get into specifics because that's not really needed for what we're covering today. And here's a step that's really important for decoders, and this is called masking. And attention is masked to block future tokens. If you think about you might have heard that ChatGPT is basically predicting the next word in a sequence. And it's pretty easy to predict the next word if you can just see the whole context, right? So because we're trying to train these models to perform something called causal autoregressive generation, so like it'll analyze it once and then append a token to it and then analyze that whole body again, we want to block the model from seeing the tokens ahead of it. And so the attention that is generated from these future tokens, there's a specific processing applied to it to make sure that the attention becomes zero. So we're not paying attention to it. To give a brief summary of transformers, self-attention carries context across tokens. Multi-head attention tracks diverse relationships, and multi-layer perceptrons preserve nonlinear relationship. So transformers are incredibly powerful because they scale incredibly well. They're all running in fully parallel computation. So if you think about it, each token embedded in each layer is running an independent computation. And it's been demonstrated that if you just scale up a model, like the performance drastically improves. So that's why, NVIDIA's so rich nowadays, because they provide the GPUs that enable these computations that power the latest AI models such as ChatGPT. So now let's look at the output step. Once we have all the attention matrices, then this final sort of, I'll just describe it as a number, is called a logit. So these values can be any integer, any negative integer, but we want sort of a probability distribution, right? We want to be able to predict with a certain probability that this token is going to come next. So here's the technique called softmaxing, which I mentioned earlier. So basically we raise the logit to the power of E, and then that's going to give us a positive number. And so it's called softmaxing because it's not simply a binary, maximum search, but it also gives weight to other tokens that aren't necessarily the maximum, but still have a decent probability. So this corresponds to the probability that that token comes next. For example, if we have a attention sequence that says that one token has, let's say, 99, that's the logit value. It's going to raise that to the power of E. So that's going to be a really big number, and we're going to divide that all over the sum. So that's going to have a very high probability that's reflected in the probability distribution. So now I'll explain autoregressive generation, which is a technique that LLMs use to generate, sequentially a piece of text. So once you've gone through one iteration of the sequence, you've found the probability that the token comes next, you'll select that high probability token and then append that to the existing sequence. And that step will rinse and repeat one token at a time, one word at a time, until a certain stop condition is reached. For example, if you're generating a story, then the story has completed. So that was a basic explanation of what LLM architectures are. I'll provide another summary. So texts are embedded into texts are turned into tokens, which are embedded into vectors and positions within the sequence. The transformer layer preserves the context, and the output layer predicts the next token probabilities. And then LLMs generate language one token at a time. And the paper that came up with this whole architecture, transformer architecture, was called Attention is All You Need. But as we learned today, attention is not all, but pretty much most of what you need. But there's some other steps that are definitely important. So these are the works cited. Thank you for listening.